All right, class, welcome back to another video here in the welding module for our class. So in this video, as promised, I'm going to start taking a little bit deeper dive into the various welding processes that we can use to do arc welding. And in this video specifically, we're going to talk about stick welding. And so we will dive into that momentarily. I do want to make a point from the last video to please make sure you take a look back at those polarities and understand what polarity means as we're moving through these welding processes, as that can play a crucial role into the setup and how effective your welds are with these various processes that we will be discussing over the next couple videos. So let's take a dive into stick welding. So I've been referring to it as stick welding. That's probably the common slang for it. But the real technical name for stick welding is shielded metal arc welding, or SMAW. That is what has been given to it by the American Welding Society. And if you're looking at welding symbols as you progress through your careers, if you see the acronym SMAW, that means that you should stick weld those particular joints. Okay, and it'll be in the tail of the welding symbol. Stick welding is the most commonly used of all arc welding processes. You'll learn why that is here in a couple of slides when we talk about the advantages and the disadvantages of stick welding. It's oftentimes used in general construction. It's used a lot in shipbuilding. It's almost exclusively used in pipelines, and it's used by a lot of farmers around the farm. It's probably the most common of the welding processes out there. And it's really the one that's been taught the most in schools. So we're going to talk a little bit about this welding process here, and as we go through this, I'm going to show you underneath the document camera how it works. So this is the stick welding process, and you can see there in bold, this is really important. It says slag must drag. So make sure you write that down, jot it down somewhere, because this welding process will produce what we call slag, which means that you have to pull the puddle during the welding process. If you push the puddle, you'll introduce impurities and create a lot of porosity in your welds. So slag must drag, which means you have to backhand or pull the welding puddle. So let's go ahead and talk a little bit about what this looks like underneath the doc cam. So here I have a stick weld that I partially did a while back. I have my electrode holder and I have my welding electrode. You can see it's fairly long in size. This happens to be a 7014 electrode. Now I'm not going to actually weld here, but I'm going to just kind of walk you through the process. So the first thing you have to do when you get ready to start welding is you have to get in a comfortable position, have your grounding clamp onto the table, and then you'll connect the electrode here to this holder. When you're ready to weld, you'll have your joint set up, and you'll come down and you will touch this electrode to the metal. So you can either do little small scrapes, little taps, or some people would do it like a match. You just do a little upward movement like this, and you will then strike the arc. So it has to manually be touched to the metal to strike the arc, but you just want to do a very light tap. Once you have that, you will then pull the welding electrode back from the metal just slightly to an arc gap that's roughly around 1/16 of an inch above the metal. Okay, so you have just a little gap there. Once you have that gap there, you have to kind of let it sit for a second and begin to create a molten puddle of metal. As this material heats up, this rod is going to also melt. So you have to continuously feed this rod downward towards the metal as you weld. So it'll heat up, it'll create a molten puddle of metal like we would expect with any other type of weld process. But this is a filler type of weld because this rod will then melt into this joint as it is melting back. So it is a filler process. While you begin to weld, you'll notice that this outside coating here, which is called flux, will be burning off in a vapor, kind of like in a vapor. So you'll see a lot of smoke that comes up off of this weld. That's the vapor from this flux. And the goal of the flux is to create an umbrella around this weld joint. Because if we think about what's in the oxygen that we breathe, it's primarily nitrogen and some other stuff as well that's in the atmosphere. Those types of things will create impurities or porosities in your weld. And so the real purpose of this flux is to create a shielding umbrella. That's why it's called shielded metal arc welding. It creates a shield around this weld joint that prevents those oxides or contaminants from entering the weld puddle. So you're going to strike the arc, create a puddle. The flux will burn off and create that umbrella, and you will drag the puddle very slowly. You can do little circles around the joint. You overlap within those. A lot of folks do zigzags across, and some people may just simply do what they call a stringer, and that slowly pull the stick across the weld joint, allowing these puddles to kind of push back up on top of themselves, creating almost like a stacked dime look. Now, the reason that you must drag this puddle is because as this begins to cool off as we weld, you'll see this substance float to the top. This substance that kind of floats to the top, it'll kind of float there and then it will solidify. And that's called slag. And slag is the impurities within the metal and other impurities within the weld that float to the top of that joint. And it also provides a little bit of insulation for the weld to cool. And so once you finish your weld with a stick welding process, you have to then do what they call chip and brush the slag to clean the joint. So you'll chip it, you'll brush it, and then you can see how well the actual weld looks underneath there. A lot of welds look really pretty until you chip them and brush them. The reason that you have to pull that puddle instead of push the puddle in this process is because that slag formation, when it forms, if you push the puddle, you'll push that slag into your welding puddle, and that will create porosity and holes within your weld. Last thing on stick welding here, when we're talking about this process, you notice that when I was showing this, I was going very slow. Stick welding is a very slow process. Compared to when you do wire welding here in lab, you'll notice you can go much quicker with that. Stick welding, you have to really slow yourself back down. And so you'll get a chance to try out stick welding here in a few weeks in the lab. Okay? Hopefully that makes sense to everyone. All right, moving on with our material here. What type of equipment do you need for stick welding? You'll need a welding power source. So you need a welder that's capable of doing stick welding. You'll need the electrode holder and a grounding clamp. You'll need a chipping brush, which is the object there on a chipping hammer and brush. The chipping hammer is the object on the far right at the bottom. Brush can be just a typical wire brush. You'll need a shade 10 or higher welding helmet, gloves, and a welding jacket. So much higher shade number here because this process does emit a lot brighter of a light. You definitely want gloves, and you're definitely going to want a welding jacket when you're doing stick welding. So going back to what I promised about the stick welding, why do a lot of folks use it? Why is it one of the most common used welding operations out there, welding processes, I should say? It's very simple, right? You have a stick, you have an electrode holder, you have a grounding clamp, and it's much cheaper. So if you go to the hardware store and buy a stick welder, you'll see they'll probably be a couple $100 cheaper than a wire welder, at least for a good quality one. So that's why a lot of farmers have always had stick welders, because they're just cheaper and they're easier to use once you get used to doing it. They can weld really thick metals, and they can weld thinner metals too, depending on the rod diameter that you use and the amperage that you set the machine at. So they're capable of a wide variety of materials. Another big advantage to stick welding, while you see it used in pipeline and other outdoor environments, is it's not as sensitive to environmental factors as other platforms. TIG welding and MIG welding in particular are very sensitive to wind, and wind blowing that shielding umbrella that I was talking about around and introducing impurities into the weld. Stick welding in particular has always been one of the top processes for using outside when welding, and that's why a lot of folks prefer that in the field. And lastly, the metal does not have to be very clean. A lot of these rods are capable of welding more rustier type metals or metals that have more impurities into them, and so that has always been an advantage, especially when you're working on older equipment. Now, disadvantages to stick welding is you have to chip and brush the slag. So that does take time. You had to manually strike the arc and maintain that arc gap with a shrinking electrode. So as I mentioned, you have to touch that electrode every time you want to start it. You have to strike it. A lot of students find it hard to strike that electrode at first. It'll stick, it'll jump around. It's kind of a pain until you learn how to do it. Newer welders do have technology now that make that a little bit easier to start, but older machines in particular, it was kind of an art to that. And then maintaining that arc gap, that's also a learned process, learning how to not only pull the puddle but also feed the rod at a consistent rate takes quite a bit of practice. So you're not only pulling it, but you're also pushing it down towards the metal. You have to stop to replace the electrodes. That takes time as well, so that all encompasses, it just results in a decreased welding speed. So if you're doing more production welding, this is probably not the best process for you. But if you're doing, outside work on older equipment, pipelines, things like that, that's what you'll be using stick welding for. So when we're stick welding, we have different types of electrodes. The electrode, again, is the stick that goes into the electrode holder, and there are different numbers associated with these electrodes, and the selection of those electrodes really depend on the base material being welded. The electrode has to be via the similar chemical composition and tensile strength of the material that you are welding. Okay, it needs to be of a higher tensile strength than what you're welding. There are rods that you can use for cast iron, for example, versus mild steel. And the position of the weld has to be considered. Some rods can only do horizontal welds. Some can do horizontal, vertical. Some can do all four of these positions that are listed here on the slide. So knowing what position you're going to weld and what material you're going to weld will set the stage for what electrodes you can use. The electrodes also depend on what type of equipment do you have. If you're looking for deep penetration, you need to use a rod that is designed for DCEP, or remember, electrode positive polarity or reverse polarity. Shallow penetrations use DCEN or straight polarity. And then general welding purposes use AC. If you look on the particular rod itself, on the case that the rods come in, or the welding electrodes come in, you will see them listed for what available polarities can they run. If you try to run a rod that does not suit the polarity that it's designed for, you'll get some crappy welds. So really pay attention to when you pick up, if it's a 6013 or 7018 rod, look at the package to see what polarities can be used. If you really need deep penetration, you need a rod that's capable of running DCEP. Okay, that's really where polarity plugs back in. The thickness of the material and the fit up, if possible, if you're welding two pieces of material together, like you saw on the paper a few minutes ago under the dot cam, you want to put those pieces of materials so that the diameter, or so that the gap between the two pieces of material is half the diameter of the electrode itself. So if you're using a 1/8 inch electrode, you want about a 1/16 gap between the material. That's important because when you're welding materials together, if you don't either bevel the edges or put angles on the edges or leave a gap, the weld will not penetrate down throughout the material. And so that while you'll weld the surface, it won't be a very solid weld. So you have to gap the material, and that's just basically what we think about when we're gapping material. If you're unable to gap material, then you want to use a grinder and bevel the material. And then your final weld appeal, how do you want it to look? That can play a little bit of a role into the electrode that you select as well. So moving into these electrodes, how do we know what a shielding metal arc welding electrode looks like, and how do we categorize it? So all of the electrodes are characterized by an E followed by a 4 to 5 digit number listed at the top of the rod. They all have a capital E, as you can see here in this designation, followed by the TTPC. So E stands for arc welding electrode. The TT stands for the minimal tensile strength in thousands of PSI. So a 6011 rod has 60,000 pounds of tensile strength. A 7018 rod has 70,000 pounds of tensile strength. The P is the welding position. If it has a 1, it can do all positions. If it has a 2 as that third number, then it can only do the flat and horizontal positions. And C stands for special characteristics, which we're not going to get into here. But mainly what I want you to be able to do is recognize this number. If you were to see an E7018 rod, I want you to know that's for a stick welding process, 70,000 pounds of tensile strength, and it can weld in all positions. So here are 4 common stick welding electrodes that you may run into. An E6011 is a rod that I used when I started welding in high school. All the high schools around my area, that's what we used. That was the standard at that time because it's what most of the farmers used. So a 6011 rod is a deep penetrating rod that can be used in any position. It can be run on AC or reverse polarity. It's used for dirty metals. So like farming instances where you might be dealing with rusty materials and stuff, 6011s are really good at that. They don't create the prettiest weld, though. It takes a lot of work to getting used to running those types of rods. A 6013 rod is a light penetrating rod with high deposition rate used at any position on any polarity. So 6013 rods don't penetrate as deep, and they are used on cleaner shop materials. So you may see 6013s being run inside of a shop on newer materials. A 6013 rod is also much easier to start than the 6011 rod. Moving into the 70,000 series, the E7014 rod is again another light penetrating rod. It has an iron coating on it, which is thick. That iron coating provides a thicker slag formation and a cleaner weld joint, not as much spatter. It can be used in any position as well, in any polarity. 7018 rod has now moved into the new industry standard. If you talk to mechanics, if you talk to folks in the field, if you talk to folks who are teaching at the high school level, they're all running 7018 rods now. The 7018 rod is a medium penetrating rod with iron powder coating, which results in a smoother arc with less spatter. So again, these rods have more iron powder in their flux. It reduces the spatter around the weld joint. They're fairly easy to get started if you realize you have to scrape the iron coating off the end of the rod so that it can actually make contact. These rods can also be used in any position, but only on AC or reverse polarity. All right. Last thing I want to mention about electrodes before we jump into this very quick video is that the diameter of the electrode does play a role in this as well. So the thicker material that you use or you're welding, you need a higher diameter or greater diameter electrode. You may use a 1/8 or 3/16 electrode. If you're using thinner materials like sheet materials, you may use a 5/32 or not 5/32. You would use a 1/16 rod or something that's much smaller in size. Okay, so let's take a look at this video real quick on shoulder mill arc welding. It is a little dated, but I think it does a good job of letting you see what's going on, and then we will wrap up stick welding from there.
Shielded arc welding is usually accomplished by means of an electric arc formed between the work and a coated metallic electrode. Let's see what happens. When the arc is struck, it almost instantly creates a temperature of about 6,500 degrees Fahrenheit. This melts both the base metal and the metal in the electrode. The metal from the electrode is melted off in tiny droplets, is carried across the arc and mixed with the molten base metal. The force of the arc and the forward travel of the electrode causes the mixed molten metal to be pushed to the rear of the crater, where it cools to form a bead. The movement of this metal toward the rear of the crater and the depth of the crater are an excellent check on the quality of the work. The operator should learn to use it as his guide. At the same time that the metal is melting, the coating on the electrode is being consumed. This takes place slower than the melting of the electrode, which shields the arc and helps direct the flow of metal. It also permits the use of higher currents, with the resultant faster deposit of weld metal. A gas is formed, covering the arc with a protective shield that prevents the exposure of the molten metal to the air and therefore prevents the formation of harmful oxides and nitrides in the deposit. Also from the coating, chemicals acting as cleansing agents enter into the metal to help to remove the impurities. These chemicals with the impurities float to the top and, cooling, form a coating or slag over the bead. This slag causes the molten metal to cool more slowly and has an annealing effect.
All right, so hopefully y'all could see how that worked. You saw the bead formation, you saw the slag float to the top right there at the end, and that would be chipped, brushed, and then removed. All right, so that's all I have for you on stick welding. Like I said, you all have a chance to do that in lab here in a few weeks. When we jump back into our next video, I'm going to discuss the 2 wire welding processes, which is flux core and MIG welding. All right, take care.